So we were doing all those sequences and series actually to understand this part. A power series is an infinite sum. Okay, so power series is an infinite sum of the form summation n equals 0 to infinity, say Cn x minus x sub 0 n. So this goes like you have constant, then you have C1 times x minus x sub 0 plus x minus x sub 0 square, okay, like this, where C0, C1 are constants, and x sub 0 is a fixed point. Okay, and the main question is here, and of course here let me add that x is a variable, and of course x is a variable. So the main question here is, for which values of x does this infinite sum make sense? So main question. For which x of x does this sum make sense? Okay, so this is the main question. So every power series of this form obviously makes sense at least at one point when you put x equals x sub 0. Everything here is 0. You just have c sub 0. So at that point always makes sense. So the question is, of course, other than that. Okay, so each. So when x equals x sub 0, the sum is C0. Okay, so we are interested, but this is trivial. Okay, we are looking for other x. Okay, so such a power series is called a power series centered at x sub 0 or power series at x sub 0. Most of the time, just for notational convenience, instead of all the time writing these parentheses, we take x sub 0 equals 0. Okay, so if you understand what happens at x sub 0 equals 0, the same techniques will apply to the others. So you just shift the coordinates a little bit, and then you obtain the general case. Okay, we already know a few examples, so let me. And of course, what are our tools when we ask a question? What do we know about these things? It's not easy to compare this with other objects because here x is variable. So we use basically the ratio test and the root test. If those tests fail, then you try to be creative. Okay. So we already have examples here. Examples of power series. So the first one, the most important one, which is always the beginning of creating other power series, is the geometric series. Okay, so let me write this one. So it is of the form n equals 0 to infinity, x to the power n. It is understood that this notation means you start with 1. Okay, so you don't ask the question, what happens when x equals 0 and I put 0. So the understanding is that this sum is of this form. Okay, so this converges if and only if absolute value of x is strictly less than 1. Okay, so This is a power series centered at the origin. All the coefficients, all the CIs are equal to 1. And we totally understand the answer to this question. For which values of x this converges. Okay? Another example is this function. Okay, so you can always invent something. So this is n factorial times x to the n. Okay. So here we take an. An is a function of x, but let me again write an. This is n factorial x to the n. Okay, so try ratio test. So we look at an plus 1 over an in absolute value. So this is n plus 1 factorial x to the power n plus 1 in absolute value divided by n factorial x to the n in absolute value. When we simplify, this is n plus 1 times absolute value of x. Now we take the limit. We take the limit as n goes to infinity. And if the limit is less than 1, it converges. If it is larger than 1, it diverges. Okay, so here you see that this goes to two things. This goes to 0 if, or let me just write this properly. Okay. So we are interested in limit n goes to infinity an plus 1 over an. This limit is equal to 0 if, okay, so let me also write that line. Limit n goes to infinity n plus 1 x. If x equals 0, the limit is 0 if x equals 0, and the limit is infinite if x is different than 0. Okay? So the series will converge if the limit is less than 1, and that occurs only at one point. Okay? So the series converges only when x equals 0. So that's, you see, the trivial case there. When x equals 0, so this one is 0 factorial is 1, the 0 power is 1, plus 1 times x, plus 2 factorial times x2, plus 3 factorial times x3. So this goes on like this. So obviously it converges when x equals 0, the sum is 1, but that's the trivial case, and this application of ratio test tells us that the series does not converge at any point. So this is one extreme case. So for the next example, let's take this n factorial to the denominator. Okay, so summation n equals 0 to infinity x to the n over n factorial. So this is 1 plus x squared over 2 factorial plus something like this. So again, let an equals xn over n factorial. We look at limit n goes to infinity of an plus 1 over an. So this is going to be limit. This is x to the power n plus 1 over n plus 1 factorial for this, and 1 over n is n factorial x to the n. So we simplify this. And here you have x, absolute value of x, and here you have n plus 1. So you see that the limit is equal to 0, no matter what the value of x is. Okay, so this is equal to 0 for all x. The limit is, for all x, the limit is less than 1, so it converges. Okay? So the series converges for all x. It will turn out that if you put a value here, it will be e to the x. Okay, so for example, we'll do this with x equals 1. Then you sum up this. If you do the infinite sum, you will have the value, exact value of e. Okay, but of course, nobody has time to add infinitely many terms. So we'll look at a few techniques which tells us how many terms we should add in order to get an approximation with error less than some pre-described quantity, epsilon. Okay, so we'll work on those things. So you see that we have three cases. It turns out that these three cases are typical. The series converges on a symmetric interval around the center. Here the center is 0. So you see that the interval here is from -1 to +1. It's symmetric around the center. We have a pathological example where the infinite sum converges only at the trivial point. It doesn't converge anywhere else. And the other case is, is this one, which tells us that the power series will converge to a finite sum no matter which x you put there. Okay? So these three cases are the only cases that we encounter. So let me do an example where the center is not 0. So let's see how we handle those cases. So for example, this is something like this. N is from, so I think I'm dividing by n. So let's start with 1 to infinity. X minus 2 to the power n divided by n. Okay, so this will illustrate a case which went unnoticed here. You see here the power series converges on the interval from -1 to +1. And because of the properties of this, we know that it doesn't converge at +1 or -1 because the general term does not go to 0. But here we understood that very easily, so it went unnoticed. So here I will show that the endpoints is one of the most important parts of power series. So here, again, we will look at an as x minus 2 to the power n divided by n. So I'll look at, okay, so let me try it here. An plus 1 over an. We know we want this absolutely. Okay, so this is x minus 2 to the power n plus 1 divided by n plus 1. And n over x minus 2 to the power n. So this is going to be n over n plus 1 times x minus 2. Okay, so when I look at limit as n goes to infinity, an plus 1 over an, so I'm looking at that limit, n over n plus 1, x minus 2. X minus 2, okay, so you see that this part goes to 1, and the limit is equal to this, x minus 2. And the series converges absolutely for all those values of x when this is less than 1. Okay, so the series converges absolutely when x minus 2 is strictly less than 1. And also we know that this is from ratio test, the series diverges if x minus 2 is larger than 1. Okay, so this part from ratio test. Okay, so you see that the ratio test tells you what's happening in this interval, outside the interval, but not at the boundary points. Okay, so we have to do the boundary points separately. Okay, so this is the case. So this is, okay, let's first do this one, what this means. Okay, so note x minus 2 less than 1 means minus 1 less than x minus 2 less than 1. So you add to all sides. So this is 1 less than x less than 3. So on the real line, you have 2 here and 1 here, 3 here. So there is convergence here. Okay, so the series converges here and diverges here and diverges here. Okay, x equals 1 and x equals 3, called the boundary points, must be checked separately. Okay, so this is a very typical example of how you deal with power series. The tests you apply, most of the time you'll apply ratio test or root test. Eventually it will end up giving you a picture like this, and there are 2 points missing. So we check those things separately. So let's see. When x equals 3, so what happens there? So you put 3 here. 3 minus 2 is 1, 1 to 2. So the numerator is 1. The series becomes summation n equals 1 to infinity, 1 over n. Okay, so it diverges. And diverges, and because it is harmonic series. And when x equals 1, the series becomes, okay, so you see that 1 minus 2 is minus 1 to the power n over n equals 1 to infinity, converges. Alternating harmonic series. Okay. So the series conclusion. So we did all these calculations because we wanted to reach this conclusion. The series converges in, so where it starts from minus 1. Okay, 1 is included, 3 is not, and diverges outside. So, okay, so this calculation is typical of any calculation you should do with the power series, because now we covered all the points. Given any point in the real line, we definitely know the behavior of the power series there. Okay, this part is called, this is called the interval of convergence. The interval of convergence. Okay. So you see that it is again symmetric around, it is symmetric around the center point. Well, the center, we see the center here. This point is the center. And the radius of convergence is symmetric around the center, except possibly at the endpoints. In this case, this endpoint is included. This is not included. This length, okay, so this length is called the radius of convergence. So you see, when you find the radius of convergence, which is in most cases easy, if you have a decent power series, you look at the ratio test, it immediately gives you, after you solve those inequalities, it immediately gives you the radius of convergence. What is missing to find the interval of convergence is checking the endpoints. Okay, so in most cases, checking the endpoints is intellectually more challenging, and practically most of the interesting behavior appears at the endpoints. For example, remember here, this one converges to, for example, ln2. Okay, so that's going to be, if you put x here, okay, so that's going to be the endpoint. Okay, so those things we'll do also separately. So let me see. Okay, so these are these examples illustrate almost everything. Well, illustrate everything that we will face. So let's put that on a theorem. Okay, so these are all the different examples we'll face. So the theorem says that that's it. So in particular, the theorem will say that there is always a symmetric interval around the center of the power series where the series converges. Outside, it diverges, and we have to look at these separately. Okay, so general behavior of summation n equals 0 to infinity Cn x minus x sub 0 n. So then one of the following hold. Then maybe here we should say only one of the following cases hold. Okay, so the first case is the easy one. The series converges for all x. Okay, so this is the ideal situation. Okay, this is the ideal situation. Once we find this, then we can work with the series quite comfortably. The other one is the pathological case. The series converges only for x equals x sub 0. Okay. Question? Question? Yeah, okay. So we had an example for this. And the other two examples we had will be given here. Okay. So there is a number. Positive, finite, such that the series converges for all x, such with the property that okay, so let us write it for all x in. This is the center. Okay, so here you see this was the center, and the radius of convergence is 1. We subtracted 1 and we added 1. So the theorem says that that wasn't an accident. That's always what's going to happen. R. And again, in that case, we have to check the behavior at the endpoints. And the series may or may not converge at the endpoints, but diverges at all other points. Okay, so in this case, we check the endpoints separately. And ratio test, in this case, told us that it diverges here. So this says that this is always the case. Okay? So here, R is called the radius of convergence. Okay, and this interval with the endpoints added, if the series converges there, is the interval of convergence. So this is all for power series. Okay, so later on you will see other series, trigonometric series. So instead of having powers of x being added, you may have cosines, sines there. Okay, for those series, this doesn't hold. Those series are used for other purposes. But what makes power series nice is this nice symmetry around the center, and inside it converges absolutely. Okay, so inside, maybe I add this. Inside means you forget the endpoints. Inside the interval of convergence, the series converges absolutely. Okay, so to note that it converges absolutely is important because later on we want to take derivatives of this term by term. Those things are allowed, and if this thing converges, well, that comes from uniform convergence. But anyway, okay, so this is the inform. And at the endpoints, absolute convergence is, of course, not guaranteed because you see here at this endpoint, this converges, and we know that it doesn't absolutely converge. Okay, its absolute value is this one. But inside, it converges absolutely. So maybe I give an idea about how to prove this. There is one main trick here, so let me do that. So the main trick in proving this is the following. So the main idea of the proof is the following. So we know that series which converge everywhere exists. We know that series which converge only one point exists. So suppose we have a series which converges at some point and which diverges. So, well, it converges at some point other than the center, and it diverges at some other point. So we are looking for we take a series which is outside of these two cases. Okay, so so assume the series converges for x equals alpha, let's say, and of course, let's take alpha different than x sub 0. So this is a non-trivial case. Okay, and then since summation Cn, okay, did I use Cn? Alpha, okay, instead of x, I'm putting alpha minus x sub 0 n converges. The only thing I know after I know the series converges is that the general term goes to 0. Okay, so that's the only thing I know. The general term goes to 0. So this becomes smaller and smaller. So for all large n, Cn times alpha minus x sub 0 n is strictly less than 1 in particular. It goes to 0. Okay, so this is, say, for n larger than or equal to n for some n. So this parenthesis is the meaning of for large n. Okay, now, so what happens is the picture is this. So here, remember what we are trying to prove. We are trying to prove this symmetry. Okay, so if it converges somewhere here, it will also converge on the other side of x sub 0. So here, suppose this is x sub 0, and suppose we found alpha here. Okay, so this is real line. So suppose we have a point here, closer to x sub 0, here or here, doesn't matter, somewhere here. So this part is minus alpha. Now I'll take any point here. Okay, so let me do that with green so that it suggests we are checking convergence. So this is x sub 0. This is alpha. And here I have minus alpha. And I'll choose some x here. I put a hole here because we'll see, well, in 2 lines, we'll see that if the series converges here, it guarantees convergence for everything in between, but not here. Okay? And in the example we had, for example, at x equals 3, the series diverged, but on the other symmetric end, it converged. So convergence or divergence at the end point does not guarantee the behavior on the other end point. Okay, so take x such that, okay, now I want to write this picture. This picture says that the distance between this x minus x sub 0 is strictly less than the distance between here. Okay, so this distance is less than this. We want to prove that the series converges here. Okay, so here all you have to do is, okay, so we take, now we'll prove this by comparison. Okay, but well, that's the only trick here. When we compare this, we are not comparing the series here with the series here, but we'll compare the series here with the geometric series using this inequality. Okay, so let's start with the Cn x minus x sub 0 n. Okay, so what happens to the general term of this? Okay, so this is the trick. You multiply and divide by the same thing. You multiply this by alpha minus x sub 0 n. So I multiply this, therefore I have to divide this. So I have x minus x sub 0 over alpha minus x sub 0 n. Okay, so I I multiplied and divided by alpha minus x sub 0. Okay, so now you see this part for large n, this is less than 1. Okay, so this part is less than 1. So this is less than x minus x sub 0 alpha minus x sub 0 n. Okay, so now using this inequality, this is a geometric series. Okay, so this is Rn, where R is less than 1. Okay, so this series converges by geometric series test. Therefore, this converges. So summation Cn x minus x sub 0 n converges absolutely. Okay, because we compared the absolute value. Converges absolutely by comparison test. Okay, so the other parts are easy. So wherever it converges, it guarantees absolute convergence for all the points inside, except possibly here. Okay? So you can take this to the end, and eventually you obtain an interval like this. And since there is a point, if it diverges here, okay, well, let me draw this as a picture. For the second part, here, what's the second part? And diverges at all other points, okay? So suppose this is x sub 0, and suppose the series diverges here, then it cannot converge here. Why? Because of this one, okay? Because if it converges here, we just proved that it will converge all the way here. So the second part is totally trivial. The only trick here is that if you are going to discover it yourself, you start playing with this, you do several things, nothing works, because you see this number here cannot be compared with this number, but there is some information, you don't know this one, for example. But after playing a while, you decide that this condition must be a key for inserting a geometric series somewhere. Okay, so these things don't come by magic. You play with these things. You use all the things you have learned, And finally, one of them works. Okay? So this is the behavior, general behavior of power series. Okay, so how do we find the radius of convergence? Of course, you use the ratio test with the general term, where you take the general term, all of this, it works. But in all these ratio tests, remember that this part comes with n to the plus 1, and then you divide it with the same thing to n. So after a while, you realize that if you work only with this one, your calculations will be simpler. Okay? So if you want to make your calculations simpler, let us solve two problems, two exercises from the book, which tell you how to get the radius of convergence. You see, the theorem tells us that the important thing is to find the radius of convergence, and then you check the endpoints. Okay? So how to find the radius of convergence for summation Cn x minus x sub 0 n. Okay, so one method is take an equals Cn x minus x sub 0 n and try ratio test or root test. Okay. If you can calculate the limit, then the limit will obviously depend on x, because nothing cancels x. Okay. And you force that to be less than 1, that will give you the radius of convergence. Okay. And the other one is just try with the Cn's here. Okay. So assume limit n goes to infinity of the absolute value of Cn, 1 over n. The only difference here is that I'm not taking this one. Okay, so I'm just looking at this one. So it's just a slight shortcut. So suppose that this limit exists and C is different than 0. Okay, then radius of convergence is 1 over C. Okay. Okay, and or 3 limit Cn plus 1 over Cn, n goes to infinity. So suppose this is C. So C can be now 0. We allow this to be 0. Also allow it to be infinite. Okay. Then R is 1 over C. Okay, so these are shortcuts for doing this. This is the basic idea is this. So I suggest that you try this instead of memorizing this, because this reciprocal is always confusing. Okay, the reciprocal comes here because in the limit, if you put also this one here, the limit will be C times x minus x sub 0. Okay, so you force that to be less than 1. So that's why this C now goes under here. Okay, so this says that if you want to memorize, you do this, but I don't suggest that you memorize such things. Take the whole thing as your general term, apply the tests you know, and from there you'll get a condition on x that will definitely give you the radius of convergence. Okay, let's do some examples. Let me see if there are interesting examples. Well, all of them are interesting, but so let's say, okay, let me start with this one. Then I'll ask if all cases of endpoint behavior appears. Okay, so problems, let's say 1. we have this series, summation n equals 0 to infinity minus 1n x minus 2n over square root n squared plus 1. Okay, so here corresponding to this Cn is minus 1 to the power n square root n squared plus 1. Okay. So we have, using these things, 1 over r is equal to limit, which one? N goes to infinity, Cn plus 1 over Cn. Okay, so now I'm doing this one. Okay, so we check this thing, limit n goes to infinity of, okay, so the only sign is this, I throw this away, square root n squared plus 1 over square root n plus 1 squared plus 1. Okay, so we take this limit, the limit is 1, okay. So this limit is 1, so you see r is equal to 1. Now, next, check the endpoint. So this is always part of the problem. Next, check the endpoints. So x equals 1. So x equals 1, the series becomes summation n equals 0 to infinity. This is minus 1, so this is just 1 over square root n squared plus 1. Does it converge or diverge? For very large n, how does it behave? For very large n, you only look at the leading term. Okay, so if this is 1 million, so you take square of 1 million and then you add 1. So ignore that. So for very large n squared plus 1 behaves like n squared. You take the square root n. So for very large n, the general term behaves like 1 over n. So it diverges. Okay, so how do we convince others? Limit comparison is easier. Okay, so well, maybe you can also check this with the, yeah, this is smaller than 1 over n, but you have to, well, whichever way you write. Here, it's easy to see that now it works, but comparison test sometimes difficult. You have to show some inequality, but taking limits for large n is most of the time easier. So this diverges by comparison or limit comparison, whichever you prefer, by the harmonic series. Okay, so let's look at the other endpoint. Here, 3 minus 2 is plus 1, so I have only this. So this is minus 1n over n squared plus 1. So somehow this behaves like alternating harmonic series, so it must converge. But that's not precise. So we have to test to this that everybody knows, and the conclusion should tell us that it converges. Now we convince ourselves that it converges because it's behaving like alternating harmonic series. Okay, so which test do we apply here? For alternating series, we have only one test. So if it works, we are lucky. If it doesn't, then we are in trouble. Now we have to find some other ingenious methods. Okay, so fortunately, the alternating series test works here because the general term without the sign is 1 over something with n. So it descends to 0. The signs are alternating, so it converges. Okay, converges by alternating series test. Well, the terminology is misleading. When we say converges by alternating series test, it it gives the false impression that the series was not convergent until the Mr. Alternating series showed up, and then the alternating series test forced the series to converge. That's not the case, of course. What we mean here that we discovered that the series converges by applying the alternating series test. But nobody wants to write all these long terms, so it's understood that we say converges by this test means that we checked using that test and the result is positive. Okay, now after these things, the conclusion. Conclusion, the radius of convergence we found is, okay, we found 1, is R equals 1. And most important one is the interval of convergence is, okay, at 1 it diverges. So this is the same as, I think we did something like this before. So at this point, okay, so we have, okay, let me stop here, then I'll continue after the break.